Hi there, this is Matt Heffernan. Welcome back to my channel. This is the 10th episode of my tutorial series on Z80 assembly language development, targeting the Sinclair ZX Spectrum to learn how to program a simple system, starting at the very lowest level. If you haven't seen the earlier episodes, I strongly encourage you to go back to my channel, and don't forget to subscribe and click the bell to be notified when the next episode comes out, and start this playlist from the beginning. So far in this series, we have learned the basics of assembly language and how each instruction for the Z80 works. Now we can move on to how assembly code can be used to make the Spectrum do different things. Most users first come to this little micro and interact with the BASIC interpreter, both to load and run software and maybe even try programming in BASIC. The ability to do this immediately after powering it on is due to the BASIC interpreter being built into the computer, burned into a ROM, or read-only memory chip, that is permanently wired into the system. We have already seen a bit on how we can use this ROM with assembly language programming as well, and in this episode we will go a bit deeper into what this ROM contains and how we can use it, or whether it's even a good idea to do so in the first place. This isn't going to be an exhaustive overview of the ROM, so if you want to know more details, I have an excellent resource for that linked in the description, as well as on the README page for this tutorial's repo on GitHub. Let's take a look at the original 48K Speccy memory map again. At the very beginning of the memory space is the 16 kilobyte ROM, so we know that any address below 4000 hex will be read-only, and always contain the same value. The rest of the memory space is writable, because it is random access memory, or RAM, and if you are quick with math, you'll see that the RAM is 48 kilobytes, as promised, even if we can't quite use all of it in any way we want. But right now, we want to take a closer look at what's actually in the ROM, so let's get a little deeper. When Sinclair made the ZX Spectrum, they were coming off the success of their previous model, the ZX81. To expedite their development, the code and data in the 8K ROM from the ZX81 was mostly reused and then expanded to include new features for the Spectrum, including support for color bitmap graphics in what was then considered high resolution. Like on the ZX81, the Spectrum ROM was fixed at address 0 for the original 16K and 48K models. But later Spectrum models would let you bank swap with another ROM that had the more sophisticated screen editor introduced with the 128K model. We won't be covering that ROM in this episode, but if you'd like to see that, let me know in the comments, and that may be a bonus episode later in the series. The ROM begins with the restarts, which we've already talked about in this series, and we'll see some more details on them shortly. Then there are regular callable routines, including the NMI service routine that needs to be at 66 hex. Then we see the first data tables in the ROM, starting with the token strings that are used for all of the basic keywords, like load and print that can be printed to the screen with a single key press. This is similar to a lot of other string collections in ROM, in that each entry can have a different length, and the string is terminated not by a special byte code, but by having the last character have its highest bit set. After that is the key table, which lists the codes read from each key for each entry mode. That is, whether you are combining it with one or both of the shift keys. Then we have more routines for the basic interpreter, broken up by the occasional bit of data. Next on that front is the semitone table, which BASIC uses for making the beeper play specific musical notes, which is definitely something that could come in handy when making your own music player. Next, we have the cassette messages that are printed when loading from tape, including the familiar start tape, then press any key. Also interspersed with the routines are tables of the control characters and editing keys, which are used for jumping to the routines that handle them. The next bit of data is a collection of messages that are used for the different error codes, and that familiar Sinclair Research copyright message you get when you power on. In between some more routines are more tables that are useful for BASIC, defining a baseline configuration for input-output channels. This gives BASIC the ability to easily use the keyboard, display, and an attached printer with simple commands. We have a couple more tables for I/O, and then some tables that help BASIC resolve the syntax of statements in a program. Then we have the tables and routines that are used for evaluating mathematical expressions, including the order of operations, in case you forgot the mnemonic you learned for that in school. After all that math stuff, we get to the end of the code in the ROM, which is followed by 1,170 unused bytes, which have all their bits set so it will look like a big sea of FFs in a hex dump. Then at the very end of ROM is where the bitmaps for 96 printable characters are stored, in order of their codes, starting with the space character, which is just 8 bytes of zeros to indicate that all 64 pixels are clear, and ending with the copyright symbol. If you are a fan of this Sinclair font, this is a handy place to get it from. After this, we have the beginning of the RAM, which starts with the screen memory, but that's for another day. For now, let's get back to those restarts. As we've seen before, restarts are special routines that can be called with the RST instruction, which can be used with one of 8 addresses that are supported by the Z80, and the Spectrum ROM has routines for each of them. Most of them are only really useful for the basic interpreter, but others can be of use to an assembly programmer. First up is Restart 0, which is what will be executed when the Spectrum is first powered up. It initializes hardware interfaces, registers, and the system variables in RAM. Restart 8 is used for error messages. That collection of report messages we saw in the ROM are what gets printed based on the error code that is found at the return address on the stack. This means to use it, the RST8 needs to be followed by an error code rather than the next instruction. The restart routine will print out the associated message and place the address following the error code on the stack for when it returns. We'll see this construct again with other ROM routines. And this kind of stack manipulation can also come in handy for your own programs when you have some fixed arguments you need to pass to a routine. You should already be familiar with Restart 10, as we have used it extensively in this series. It simply prints out the character code in A at the current cursor, or executes a control code, like how Enter will move the cursor to the beginning of the next line. Restarts 18 and 20 work together to collect characters from a RAM buffer. This is really only useful to the basic interpreter. Restart 28 runs a calculator routine, which is specified by a sequence of operations starting at the return address, similar to how the error restart gets its code. However, you can have an indefinite number of operation codes before getting back to regular Z80 instructions, as this routine will keep executing until it sees the code for ending the calculation. It uses a stack similar to Forth or an old HP calculator, if you are familiar with those, and the top 2 elements on the stack are specified by the HL and DE registers. To use it, you follow the RST28 with different codes that execute routines specified by the calculator address table we saw earlier. It will keep going until it sees the hex 38 code, which will return back to normal execution. The use of this calculator feature is very complicated, and it deserves to have its own future episode. Let's move on to the rest of the restarts, starting with RST30, which is used to allocate a number of spaces specified in the BC register in the basic workspace. Dealing with that is something you probably don't want to do in an assembly language program, where you're better off managing your own memory, usually with fixed allocation. Then we come to the last restart, which by definition needs to be the maskable interrupt routine for interrupt mode 1, like we discussed in our previous lesson. The Spectrum goes in interrupt mode 1 at startup, so this will be executed automatically at the beginning of every vertical blanking period, 50 times a second to accommodate PAL TV signals. You can still call this routine on your own, especially if you want the same process to be executed during an interrupt mode 2 routine. It's not required, but if you do call it, the following things will happen. The frame counter in RAM will be incremented, which is among the system variables. The low byte is referred to directly by its address, while the upper byte is assumed to be at a fixed offset from the address in the IY register. If you go messing with IY while in interrupt mode 1, you'll see increments happening at seemingly random places every 256 frames, so good luck debugging that. The keyboard scanner is also executed, and maskable interrupts are enabled, so you can use an RST38 to kickstart the interrupt cycle. With all the restarts out of the way, let's take a closer look at the keyboard scan that RST38 does. You can call it at any time in case you don't want to wait until the next frame by doing a call 02BF. This will populate the keyboard state variables at the beginning of the basic reserved RAM. Then you can call the keyboard input routine at 10A8 to retrieve the code of the last key that was pressed and place it in the accumulator. If that key was still being pressed during the last scan, the carry bit will also be set, so you can just keep calling this routine while your interrupts are triggering keyboard scans, and jump out of that loop when carry is set to process the new keystroke. We'll see how that works later in the example program. But before we get to that, we need to ask ourselves whether we want to even use the ROM in the first place. Sinclair only intended that ROM to be used by the BASIC interpreter, and assumed that anyone supplying a machine code program would do everything on their own. As a result, most games that have graphics don't even bother with a ROM, or maybe only make use of some of the data or a routine or two. When you go about making your own program, you're going to have to weigh out the pros and cons of using the ROM. The biggest pro is the one we've been taking advantage of extensively in this video series, and that's the ability to easily print characters to the screen. And that's great if you're doing something exclusively text-based. But the con is that the ROM won't be much help when it comes to graphics, or if you want to have a different font or place text in arbitrary places on the screen. The ROM does give you a very simplified keyboard interface, but it has the same problem as the BASIC interpreter, in that it only responds to a single key press in any given frame. You may not be able to type quickly on the original dead flesh rubber keyboard, but the poor response you see on later keyboards or in emulation is not desirable for gaming, and you'll be better off reading the key states directly from the input port. The built-in calculator is great if you want to do floating point operations and not have to roll your own library and have it take up precious RAM space. But the reality is that fixed point math is much faster and will probably be adequate for whatever you're trying to do in a game. Chances are you're not watching this series to make your own 8-bit spreadsheet program. Finally, the ROM is code that has been tested and proven over 4 decades and is well understood by other Spectrum developers. Unfortunately, most developers are just making games, so only a small minority of them really know anything about the ROM. If you choose to use ROM routines and not just read the data, there are certain limitations you need to stay within to prevent catastrophic errors. First, you don't have unlimited use of registers. These routines expect certain values to be in the alternate HL register and in the Y register, like we saw already. Calling a ROM routine, or even letting the interrupt mode 1 routine run while those registers have been modified, can bring everything to a crashing halt or introduce some very weird behavior. The same goes for the RAM being used by those routines, which starts at 5B00. If you don't use the routines, then you can have that memory to use however you wish. When you only have 48K of RAM, you don't want to sacrifice any more than you have to. But if you had 128K, like on a later model, you have the added complication of having banked ROM. You can't assume the 48K basic ROM is always banked in, and with interrupts thrown into the mix, things can get a bit complicated. And finally, the big difference between the Spectrum and its American clone, the Timex Sinclair 2068, beyond the video standard, is the ROM, which is not compatible. So any software that depends on the ROM needs to be rewritten to be ported. But for the purpose of this lesson, let's go ahead and use the ROM to make a simple typewriter program that will let you just type on the screen and let you change the color of what you're typing on the fly. Let's get into the code right now. As usual, we start our assembly code file by specifying the 48K Spectrum as our target machine and beginning our code at hex 8000. We don't need any data, but we do need to define some constants to make the code a little more readable. We're going to be using the clear all and keyboard input routines in the ROM, so we have those addresses. Then we define the range of characters that we will print, from space to the copyright symbol. Then we need to define some special control codes that we'll be using. Then we start our code by making sure we're in interrupt mode 1 and enabling interrupts. Then we can call clear all to make our whole screen the paper color and place the cursor at the upper left corner. Now we're ready to start waiting for keystrokes, which we do by calling the keyboard input routine and then looping back to call it again until the carry bit is set, indicating a new keystroke. We first compare the code to the @ token, which will be entered by holding down the symbol Shift key and pressing I. We're going to use this for setting a new ink color, so if that happens, we jump ahead to Do Ink. Otherwise, we check to see if it's the only control code that we will process as intended, the Enter key, which we go ahead and print to move the cursor to the next line. At this point, the only other keystrokes that we will use must be for printable characters. So we go back to the top of the loop if it's less than the space code or greater than the copyright character code. Otherwise, we go ahead and print it. Now, if we saw that symbol I earlier, we jumped ahead to here where we print out the ink control code. This won't actually print anything visible. Instead, the ROM code will wait for you to print a color value. So we want the user to press a number key between 0 and 7 to select an ink color. This means we need another loop to wait for that keystroke. So we keep calling keyboard input until the carry bit is set, and then we see if it was a valid entry. If it's less than the 0 character code or greater than the 7 character code, we jump ahead to reset ink, where we change the color back to black. But if it is in range, we subtract hex 30 to get the number value, and then print that. Because the last code printed was the ink code, this new value loaded into A will be interpreted by the ROM as an argument value, rather than its normal control code. So printing out a value of 6 in this state will change the ink color to yellow, rather than being interpreted as a caps lock as it would normally. With the value we need, we can jump ahead to print it. But if we didn't hit one of the valid color keys, we jump to this point where we just load a 0 into A so that the ink color will be set to black when we continue on to print it. Now that either the last character or control sequence has been printed, we can go back to the top of the loop and wait for the next keystroke, which we'll just keep doing indefinitely. If you don't like the Spectrum being a dumb typewriter, you can always just cycle the power, which is the great thing about these old micros. We'll deploy this code by generating a snapshot named rom.sna. And to do this, we have a build script. We just call sjasm plus with the LST option to generate a machine code listing, and then pass it the name of our assembly file, rom.asm. Now let's go to the terminal and run it. We run build.sh, and then do a directory listing, and we can see that the rom.sna snapshot file is there. So let's load it into the emulator. We're using Fuse again, so we hit F3 and select rom.sna and run it. Now we get a blank screen, so let's start typing. The default colors are dark with black ink on white paper, which comes out gray because of the darkness. Then if we hold down a control key with the emulator, that will be treated like the symbol shift key. So then pressing I will get us into the state of waiting for an ink color. Hitting the 1 key will change the color to blue, which we can see by starting to type again. We can try other colors, and we can see each of them take the expected effect, even color 7, which is white. You can't see it right now, but I am typing, but it's just white ink on white paper, so it's invisible. Doing Control I followed by a 0 makes the ink black again, and we can just keep typing until we get bored. When you build this, try going back and implementing new features, like paper color selection or graphics characters. In the link GitHub repo, you'll find not only this code, but all of the code examples for each lesson, and all of the slides presented in this series. In the README, you'll also find links to some additional materials that can help explain what's going on, and provide some needed background in case your programming experience is a bit limited. Please subscribe to my channel and click the bell to be notified when the next episode comes out. And please like this video if you learned anything, and let YouTube know that you want to see more tutorials like this. If you can't wait for the next episode to go public, join our Patreon community and see my videos ad-free as soon as they are uploaded, just like the people you see here. Thanks for watching, and I hope to see you again soon. Bye-bye.